Hey, good morning or good afternoon or good evening, depending upon where are you dialing from, if dialing from overseas. My name is Vivek Dua, and I'm based in the Department of Chemical Engineering at University College London. So what I'll do today is give you an overview of process systems engineering approaches for solving complex healthcare systems engineering problems. Uh, I mean, we know how the current situation is, and healthcare has become more important than ever before. If you look at these graphs, which show the UK expenditure on health, on the left is in billions of pounds, and this amount has increased steadily over the years. And on the right is the graph which shows the healthcare expenditure as a percentage of GDP, which also has an onwards increasing trend. And this is before the current situation related to Corona emerged. So you can imagine how important it is for the governments uh, of the various countries to provide uh, improved quality of life for patients, and how much pressure this is putting on the economics of the economies of various countries and companies across the world. So it's quite important to improve the quality of life of patients, but at reduced costs. We would like to do this in a cost-effective manner. This is a very complex challenge, and solving these healthcare engineering problems requires collaborations across various disciplines. So it requires an interdisciplinary approach involving doctors, engineers, and scientists. Okay, so the view we take is that we cannot solve this problem alone. We need to collaborate with others. And at UCL and in my department, we collaborate with doctors and various hospitals associated with UCL and other hospitals and doctors as well. We collaborate with other engineering departments, and we also have very excellent collaborations with other science departments at UCL and other universities. So this essentially requires a very highly collaborative effort, because this is actually a very complicated and complex problem. So when we collaborate with people from different domains and disciplines, we need to understand their language. So for example, if you are working with somebody who is working at cellular level or organ level, or somebody who is interested in manufacturing devices, medical devices, and then there are people or experts working with large amounts of data to develop computational models. So domain expertise is quite important, to understand that domain expertise and to be able to translate into a problem that we can understand, formulate, and solve. So to put this all together requires a systems approach, okay? So it's not just looking at one cell or a particular type of organ, but how it fits into the holistic picture of the complex healthcare engineering problem we would like to solve. Okay, so in the department, we have a very highly reputed and research active group in the area of process systems engineering, where we are involved in developing techniques and models to solve complex problems such as the ones which arise in healthcare engineering. Here I have provided you a glimpse of the type of problems that we work with: linear and nonlinear optimization, parameter estimation of dynamic systems, machine learning, and as you know, artificial intelligence is quite popular nowadays, model reduction, because we end up with very large complex models involving thousands and millions of variables, which cannot be solved in a reasonable amount of time. So we need to reduce them to models that we can deal with effectively and efficiently. And optimization under uncertainty, once we have a model of a complex problem, how do we solve that problem to optimize the outcomes in terms of making sure that our processes that we are looking at, whether they are healthcare processes or chemical engineering processes, are designed and operated in a cost-effective and economic and safe manner, while taking into account the various uncertain parameters which exist because of the simplifications that we build into the model, or the uncertainty that exists around the world, around the globe. And fault detection and process control is mainly concerned with making sure that whatever uh, systems that we design, uh, whenever there is a fault or there is a malfunction, we are able to detect it quickly and ensure that we are able to control that process and bring it to a safe operating region, and many more. So I've just given you a glimpse, but there's a lot more that is going on in the department. So I will kick off by a, I will show you a number of examples, healthcare engineering related examples. So let me kick off by a specific healthcare problem, which is cystic fibrosis. It is a genetic disorder. Uh, what you see on the left is sort of a pictorial representation of what is happening in a normal epithelial cell. You don't need to worry about too much details. I mean, there's a lot of literature available out there, that you can read. But I would not go into too much detail at this stage. What I would like you to give you is an overview of what this problem is and why process systems engineering is important to deal with such problems. Okay. So this is a typical epithelial cell. There is a sodium channel on the top and a chloride channel, and there are a number of ion channels and transporters at the bottom. So this is known as the apical layer, and this is known as the basolateral layer. On top of this epithelial cell are these cilia-like structures. These are hair-like structures. They are known as cilia. And this blue thing is the water layer in which this cilia is immersed. Okay. And on top of this uh, water layer is the mucus. Uh, so what happens in a typical normal or healthy person is that when we breathe air, the mucus gets developed, and this cilia, it beats. So it continuously beats in a regular fashion, and it kicks the mucus out, and it keeps this epithelial layer clean. But for patients who are suffering from cystic fibrosis, there has been a long debate going on that does this why do they suffer from cystic fibrosis? So one of the hypotheses is that their chloride channel does not function very well. So and this results in water being absorbed from the water layer into the cell. Once the water is absorbed into the cell, this reduces the thickness of the water layer. And because the thickness of the water layer is reduced, the cilia is not able to beat continuously. And because it is not able to beat continuously, the mucus starts building up, and it cannot keep the mucus layer clean. And then it results in infections, and then the patients have to live on antibiotics for a long periods of time, and their life expectancy is on average around 40 years. Okay. So there has been a long debate on regarding is this just a chloride channel? So why does this happen? So we were looking at this, and we hypothesized that it's not just the chloride channel. What about the sodium channel? Does it play a role or not? And it is very difficult to investigate this without actually going into looking at this mechanism from a systems point of view. You can look at the chloride channel, you can look at the sodium channel, you can look at the potassium channel, but unless and until you put everything together and take a systems view, take a holistic view of what is happening around the cell, it is very difficult to make any conclusions. So what we did is we had some experimental data, which basically has a perfusing solution going at the top, and these are the epithelial cells, which I showed you earlier. So this is an epithelial cell layer, and then we measure the potential difference across the epithelial cell layer. Okay, once we have that experimental data, we developed a mathematical model. Again, you don't have to worry about the details. What I'm trying to show you here is an overview or a glimpse of a systems approach. So we wrote mass balances for various components that exist in the cell. For example, the sodium, the chloride, the potassium, the voltages, and so on, and the cell volume. Okay, so the model is actually much more complex than you can see here. And so I'm just giving you an overview. So, and this model is then is sort of an equivalent to an ordinary differential equation model, dx by dt, which is a function of x, t, and some parameters p. So these parameters are, for example, if I go back to the previous slide, how effectively the sodium and chloride channels behave. Okay, also this is for example, the permeability of the sodium channel and the chloride channel. So if we now, if we have that model, if we can solve that model, and then we compare the permeabilities of sodium and chloride channel for a healthy person with that of a person who has cystic fibrosis, we might be able to draw some conclusions. Let's see, can we? Okay, so what we did is that we used the data, hypothesized what is actually happening in the epithelial cell, developed a mathematical or computational model, and then we try to fit that model with the experimental data that we obtained. And the idea is to be able to draw some biological conclusions that we would have not done otherwise. Okay, so this shows basically how the experimental data behaves. This is the hypothesis that we developed, that we have chlorides and sodium channels, the mathematical model. And this graph on the right-hand side shows that the permeability of the sodium channel for CF patients is higher than that for non-CF patients. Okay, let me just. Okay. So based upon this graph and the mathematical model that we developed, we are able to say that the loss of chloride channel permeability alone is not sufficient to explain the cystic fibrosis that we observe in patients with CF. Okay, there has to be an increase of sodium permeability in the apical layer. And this conclusion is based upon the mathematical model that we developed. And although there was a lot of discussion and controversy on that it's only the chloride channel, but we are able to show that mathematically that just the malfunctioning of chloride channel is not sufficient. And this is a very important conclusion, because now the pharmaceutical industries, they can decide where to focus on. Then they now know that if they're going to develop a drug, they should not just be focusing on the chloride channel. They have other options to work on as well if they're trying to identify a target drug for CF patients. Okay, so now going to move to the next application. Now, once for example, a pharma company has decided that, okay, they are going to develop a particular drug for a particular disease, and it requires a fermentation process, and they want to operate that fermentation process in a cost-effective way and in a safe way, and so as to maximize the yield, they have to do their process dynamics and control analysis quite carefully, because these fermentation processes can go wrong suddenly, and it takes several days to for these fermentation processes to complete. So for example, if a fermented batch fermentation process has started, and after a few days it turns out that something has gone wrong in the fermentation, they have to just throw the batch. So it's a waste of material, money, and waste of time. So again, if you look at this from a systems point of view, what we would like to do is we would like to detect the fault as quickly as possible. So here what we did was we had a mathematical model which involved some measurements such as concentration of biomass, product, and substrate, and we propose that we can detect any faults by calculating the model parameters, which in this case were mu p and mu m and yp. So mu m stands for maximum growth rate of the biomass, and yp for the yield coefficient of the product. Now, there have been quite a few approaches which have already been proposed in the literature, but the key contribution of our work was that we obtain model parameters as a function of system measurement. So as soon as we get the system measurement, and if there is something going wrong, we can quickly identify and report that a fault has been detected. And we carried out a few case studies where here I've showed our fault 1, 2, 3, and 4 corresponding to different faults that occurred in the fermentation process. So what you see here is that as the time passes, we can detect a fault which occurred at 5 hours. And this was detected by monitoring the model parameters, which I mentioned in the previous slide, mu m and yp. So this is the nominal or the true value of mu m, and this is the nominal or the true value of yp. But as soon as the fault occurs, these values change, and we are able to detect that very quickly. Okay, and this is quite important because, as you know, there is a lot of effort going on, manufacturing vaccines fast and quickly, have a quick turnaround, have a large production. We would not like to have faulty batches or throw away a lot of material in such difficult times and situation. We would like to have a good turnaround. Okay. Now, another application that I would like to allude you to is to do with people who are suffering from chronic renal failure. So what happens in our body is, when we eat food, the food gets metabolized, a lot of metabolites and other toxic materials and other salts which are generated, and they should be quickly and regularly removed from the blood. For people suffering from renal failure, chronic renal failure, this does not happen, and they have to go for hemodialysis, which requires going to a hospital setting, usually 3 times a week for around 3 hours. So it is quite inconvenient, and it is not let's say, a foolproof process. You require a lot of human intervention. The doctor, the nurse have to stand there and monitor them so that everything is going well. So basically what happens is the blood is taken out from their body. It goes to a filtration unit where all the toxic elements and salts are removed, and then an iron and water balance is adjusted, and then the blood is recirculated back to the body. Okay, so this picture basically shows what I just described, that the blood goes from the body into the hemodialysis machine, gets cleaned, and then the clean blood is recirculated back. So this again is a systems engineering problem, because we're looking at the human body, we're looking at its interaction with the dialyzer, where a chemical engineering process of separation and mass balance is taking place. and then the clean blood is recirculated back to the human body. So there are quite a few interactions taking place. Now, this basically the idea is to make sure that all this happens safely, because there can be complications during hemodialysis. If the filtration takes place too quickly, um, and suddenly the water level goes down in the body, it has very negative health impacts. We would, and for example, if the salt levels are adjusted too quickly or um, are not adjusted within certain lower and upper bounds, these also have very negative health impacts on the human body. So this now again is a, if you think from a chemical engineer's point of view, is a process control problem. Okay, so so what we have done is we have put together again a mathematical model of the system, which I'm not showing. That's a very complicated model. And then we developed an artificial neural network approach to solve this model, so as to make sure the profile of the hemodialysis operation tracks a safe profile and keeps everything within bounds. Obviously, hospitals would like to reduce cost so that the patients come for as few hours as possible to the hospital. But we, but they, but obviously they would like to do it as safely as possible. We would not like to do it too fast to endanger the life of the patient. We would, but on the other hand, we would not like to make it so slow that it's a waste of time, not only for the doctors and nurses, but also for the patients. Okay, they have to also go back and get on with their lives. So, these graphs essentially show that um, the results that we obtained from the model that we developed. So these straight lines or dotted lines are our model predictions, and these square boxes are the experimental observation. So you can see there's a quite nice match between our model predictions and the experimental data that we obtained. Okay, once we did that, once we obtained this model, then we have also now extended it to actually calculate optimal rates at which the blood should be removed and recycled back to the body, and the rate at which the uh, the ionic solution in the dialysis should be adjusted. Okay, so we have done all those work as well, which I'm not showing here, uh, just to keep things simple. Now, the final application that I would like to discuss is regarding gene therapy, and it again is a very interesting process and chemical engineering problem. So gene therapy is quite useful because what we would like to do is treat patients who have certain genetic disorders, and some of the genes are malfunctioning. So what the basic idea, from systems point of view, is that so this blue thing is the cell with endosome, cytoplasm, and nucleus. And nucleus is where we would like to take this corrected gene. So there is a faulty gene here, and what we would like to do is take this blue gene or the genetic material, which is a corrected gene, and transport it into the nucleus. Once that is done, and there is a corrected gene in the nucleus, it will produce cells with the corrected gene, hopefully. Now, the barrier is that this gene cannot be directly, put into the cell so easily. So it is encapsulated in a carrier, which carries it to the cell wall, and because of the properties this carrier has, it is able to cross the barrier of the cell wall and then eventually end up in the cell and slowly into the nucleus. But everything that ends up inside the cell does not necessarily end up in the nucleus. It might get degraded or just lost in the cytoplasm. So there is a loss of efficiency here as well. So what we have done again here is developed a mathematical model, and we have shown that by manipulating the rate at which this uh, uh, gene encapsulated in the carrier is infused, we can make sure that a reasonable amount of genetic material is transported to the nucleus. Now, the challenge here is that, okay, we are, one could simply say that just increase the amount or the concentration of this material, and eventually a lot will flow into the cell. The problem here is that this purple material, uh, uh, which is the carrier, when it ends up in the cell, it has some toxic properties. So this transport is not for free. By free, I mean it's not free of toxicity or side effects. Okay, so you cannot just have a lot of that material. So you need to make sure that there is an optimal amount of material transported. Okay. So as I mentioned earlier, we have developed this mathematical model, which I'm not going to go into the detail, but just to show you glimpse of what sort of mathematical model it looks like. So what we have here is a trade-off. So you would like to increase the effect or the amount of genetic material entering the nucleus, but as you can see from this dots or the diamond points that I have here, that as we try to increase the effect, the toxicity also increases. Okay, so there is a clear trade-off between efficacy and toxicity, and this needs to be balanced while we're deciding upon the dose that should be given to the patient, or at the rate at which it should be infused into the patient. Okay, so what I've done is sort of given you an overview of the systems engineering approaches that we are researching in the department, and you know told you a little bit about cystic fibrosis, hemodialysis, fault detection, and gene therapy. But I'm not the only one working in healthcare systems engineering. We have a 10 strong academic group in the academics group in the department, and they're working on a number of problems related to healthcare engineering. And we don't have time to go through all of them, but just for you to know, or just for your awareness, that there's a lot going in the department, and we have collaborations with other departments and institutes as well working on this type of problems. And we have collaborations with hospitals, and a number of process systems engineering approaches, which I mentioned, are actually taught during various modules in the department. I'm involved myself in teaching a few of those modules. For example, in the first year, I teach computational modeling and analysis, where we look at linear programming, modeling of dynamic systems, degree of freedom analysis, and how we can translate, mass balance equations uh, into models that we can solve to address interesting and challenging problems. Then in the third year, I'm involved in teaching process dynamics and control, which looks at some of the aspects where things are changing quite quickly. There's disturbance in the system, how we can make sure that the process is safe and works in a controlled manner. And then there are other modules which are taught by my colleagues. For example, there is a fourth year option of advanced process optimization, where advanced optimization techniques are taught, including mixed integer, nonlinear programming, and so on. And then there is a fourth year module on advanced process modeling and design, where advanced dynamic modeling tools are looked at. Okay, so just to summarize, so healthcare engineering problems involve uh, many complicated and complex aspects, and it's not always useful to just look at one aspect. It's quite important to look at from a systems point of view, how disease is being developed, how it spreads, let's say within the body or between people, like pandemics, how we can prevent it, how we can diagnose it. There are some diagnostic tools being developed. And then once we have a good understanding of the disease, how we can develop therapies to treat those diseases. Keeping in mind that there is, while we might come up with a very nice, effective molecule that can treat the disease, but if it has very negative other side effects or is highly toxic, it may not be the drug that we will see in the end. So we have to keep everything in mind. Okay, and this is what is a key aspect or a key spirit of process systems engineering approach, which takes a holistic view of the problem, and it also enables manufacturing various drugs, devices, and so on. Okay, with that, I will conclude. And thank you for listening. And I'll be happy to take any questions you might have. Okay, I have a couple of questions here. So I'll read out the first question. It says, you previously mentioned that fermentation takes a few days before the process is finished. And if something goes wrong, then you would just throw the batch away. So you created a fast fault detection of the system. But then how would you mitigate the situation? How would you control the system that's ongoing? Okay, that's a very good and interesting question. So basically, this what I mentioned was that typically this is what used to happen in the past, that you would simply throw the batch. But now, if the advantage of developing a technique where you can detect the fault very quickly and very fast is that before things become disastrous or go to a point of no return, you can take action. So you can make changes to the system. For example, if you want to slightly change the temperature or the pressure or the oxygen content, you can quickly do that so that and that's how you would mitigate such a situation. Uh, The second question is, how long does it typically take at each stage? Also, what stage do engineers find the most challenging when solving healthcare engineering problems? Okay, I'm not sure by what stage is the question. I mean, what do you mean by each stage? Probably if it is to do with the various stages of understanding the disease, developing the drug, manufacturing the drug, then I would say it is really specific to the problem that you're looking at. So, for example, it takes quite a while to develop mathematical models to collect the data. So, experimental part is quite time consuming. And then developing a mathematical model to actually capture that experimental data into a mathematical model and then analyzing the results. So each of these stages is quite it takes quite a while. So it could take, for example, months and years for each of those stages. The second question is quite interesting. That which is the most challenging? I think it's quite it depends who is looking at it. For example, uh, if it is a systems aspect that we're looking at, I would find it most interesting. But for example, it is something which is not that systems interesting. Uh, it, then that would be most challenging for me. And I think one of the key challenges that we face when we are solving these healthcare engineering problems is being able to communicate with other disciplines and domains, because we all have our own languages. We understand, our own domain language. But when we have to talk to doctors, or we have to talk to scientists, or when we have to talk to policymakers, they see things differently, and they have a different language to the problem. So I think language is one of the key challenges, I would say. Okay, the Now, the third question is, how is the healthcare systems engineering model applied to COVID? What stage are we currently on? Okay, I don't have an answer to that question. I don't think, it, I think a lot of work is going on, and it is changing uh, day by day. There's so much, there's so many calls coming from research councils and pharma companies, and they're working really, really hard. I think, I mean, I can't bet on that, but I think the estimates are that the vaccine will come out in about a year's time or so. Okay. Mm. Okay, the next question is it possible for the genes in gene therapy to be given to specific cells and organs? Yes, I mean, that is how they're typically designed. So the carriers are designed to target specific cells and organs, but obviously, while they travel from one part to the other, there are certain interactions with other parts of the body unless you inject directly into certain parts of the body. So the answer is yes, it depends upon the disease. In certain cases, yes, but not always. Okay, the next question. Okay, the last question is quite interesting, and it's quite topical as well. For example, the problem with hemodialysis is it okay, where did it go? Is it possible to enhance the system through a computer-aided sort of machine learning process to self-optimize the process? By putting the system through an AI learning curve, would it be more efficient way to develop the process? Uh, okay, so there are AI-based approaches. So obviously there are advantages and disadvantages of AI. So artificial intelligence works extensively based upon the data that you have. So it does not necessarily go into, for example, the details of the mass balance of the ions. Uh, so yes, it can help. AI can help the learning curve, and it can actually help personalize the hemodialysis machine to a specific patient. But it is quite important to understand the basics of the basic fundamentals of how the ion exchange is taking place. Because if something goes wrong and if it doesn't work, it is very difficult to diagnose just based upon the AI why it didn't work. So a combination of model-based approach and AI or data-based approach is the way forward in my personal view. Okay, the next question is actually very similar to the previous one, which is, can AI be used in these healthcare engineering systems? And will it go hand in hand with chemical, mechanical, electronic engineering in medicine? I mean, as I said, yes. I mean, for problems where we do not have a good fundamental understanding, I think AI is quite useful. The only thing we have to keep in mind is that we need to provide large amounts of data. Uh, so my personal view is that AI alone or modeling alone, uh, which requires very complex models, which may not be solvable in reasonable amount of time, may not be able to solve this problem individually. But when we put together uh, the weaknesses, I mean, of modeling and AI, and we use them, in a complementary way. I think they can go a long way. Okay, I have another question. Could you re-explain about the fast fall detection? What are the faulty scenarios that you use in research, and why do you use mu-m and yp as the parameters to detect the fault? Okay, so what I have shown here is a specific example, because what we have developed is an approach where we can obtain, let's say, certain characteristics of a process as a measurement uh, of from the process. Okay, typically what is done is you take lots of measurements and then you solve a complicated model, and by the time you solve the model and uh, identify what has gone wrong, it takes a lot of time. So our contribution here is that we have obtained the parameters, model parameters, which which would go wrong as the system tries to malfunction, and we want to identify those quickly. Okay, there was a reference at the bottom of that presentation, and you can have a detailed look at the model there and the references there, and if you want to really dig into it, or send me an email, and then I can explain this in a much more detailed way, giving more references. I mean, we don't have time to go through the theoretical aspects behind this one, but just to summarize, um, we obtain model parameters which correspond to, or which actually tell you whether the system is behaving nicely or not, whether it's faulty or not, as a function of system measurements, and do this quickly. Okay, there's another question. In the gene therapy part of the lecture, is it possible to remove the carrier before the gene enters the cell to reduce the toxic effects? Thank you. Okay, so the answer is no, because if you remove the carrier before it enters the cell, it won't be able to enter the cell. The purpose of the carrier is to uh, provide that, let's say, lowering of the barrier facility to be able to go into the gene. And the last question here is, how would you provide such a large data to train the AI when the systems we are facing is dynamic? Okay, I'm not sure if I understand the question. I mean, if the question is related to the fact that how would we train AI if the amount of data is large, then I would say that's not a problem. I mean, you might have seen some of the deep learning research that has happened in the past few years, and how major companies are using it. So there has been a tremendous progress in AI, deep learning, and data systems engineering in the past few years. So that's not a problem. Are there any other questions? Okay, I have one more question. How effective is AI in detecting faults in healthcare engineering problems? It is quite effective, and it's used quite a lot. Uh, now the question really is, where do we draw the line about healthcare engineering? So healthcare engineering spans many applications. So in certain applications, it has been very effective and it is used a lot. but not so much in certain other applications. So it's very, so things like these. So one thing I would like to emphasize is that all the tools and technology that I mentioned regarding process systems engineering, we have to be very careful about what sort of tool are we using for what sort of application. So in certain applications, certain process systems engineering tools are very effective, and we have to have that basic knowledge to be able to pick those tools. And once we have that, let's say, expertise and knowledge developed, you can essentially say, okay, these type of techniques are likely to work better for these type of problems, and vice versa. Okay, are there any other questions? Okay, I don't see any open questions. And with this, I would like to thank you all for dialing in. And I wish you all the best. Stay safe. Take care. Bye bye. This is Vivek Dua signing out.